Hello students, welcome you all for the next problem on Otto cycle. So the question states that engine working on Otto cycle has the volume of 0.45 meter cube, pressure 1 bar and temperature 30 degrees Celsius at the beginning of the compression stroke, which means the data provided here are for the state of 1. So we are taking these values as V1, P1 and T1. At the end of the compression stroke, the pressure is 11 bar, which is going to be the P2 value, and 210 kilojoule of heat is added at a constant volume. So this is going to be the heat supplied or heat added. What we need to determine is the pressure, temperature and volume at salient points in cycle, percentage of clearance volume, efficiency, net work per cycle, mean effective pressure, ideal power developed by the engine if the number of working cycles is per minute is 210. Assume the cycle is reversible. So since the working fluid is not mentioned over here, it is taken for granted that air is going to be used, and for air gamma is going to be 1.4. Okay, so firstly we need to solve, or we need to have the values of all the parameters at salient points, which is point 0.1, point 0.2, point 0.3 and point 0.4. So here we need to know all the values of pressure, volume and temperature. Okay, for that we are going to make use of the processes from the thermodynamics. So here the process 1 to 2 is reversible adiabatic process, so in which we can say that it is governed by the equation of PV power gamma equal to constant. So for process 1 to 2 I can write P1 V1 power gamma is equal to P2 V2 power gamma. From this we can arrive at a simpler versions, like putting things apart. I'll write V1 by V2 power gamma is equal to P2 by P1, and if I bring this gamma to the other side, I can state that V1 by V2 is equal to P2 by P1 power 1 by gamma. Why? Because is that we know that V1 by V2 is going to be R, that is the compression ratio. Since we don't know the volume of V2, we are going to use the other relation in terms of pressure, which is P2 by P1. We know the values of P1 and P2 since it is provided in the question paper itself. So the value of P2 is going to be 11 bar, and value of P1 is, sorry, pressure of P1 is going to be 1 bar. So in substitution process, what we need to do is we need to convert it into kilopascal or kilonewton per meter squared. So I'm going to just multiply it by 100. So 100 kilopascal, whereas for 11 it is going to be 1100 kilopascal. So if I substitute these values, okay, so 1100 divided by 100 whole power 1 by 1.4. If I substitute these values and make some simple simplifications, I can write that 11 power 1, 11 power 1 by 1.4, which will have the value of around 5.5. Okay, so this is going to be my R. So knowing the value of R, I can write that R is equal to V1 by V2, and R is going to be my 5.5, which is equal to V1 value we already known, which is given in the question paper, 0.45 meter cube. So which is going to be 0.45 divided by V2. If I do some simplifications, I'll get this V2 going to be 0.45 divided by 5.5, and the value arrives to be 0.0818 meter cube. Okay, so this is going to be V2, and in to measure or to calculate the value of T2, we know yet another relation for reversible adiabatic process, which is T2 by T1 is equal to V1 by V2 whole power gamma minus 1. Okay, why I am using volume? We can write instead of V1 by V2, I can write it the value of R, which is 5.5. Okay, so substituting the values known, T2 is unknown to us and T1 is provided in the question, which is 30 degrees Celsius. Converting it into Kelvin, we are adding 273, so it gives a value of 303 Kelvin. So T2 by 303 is equal to, instead of V1 by V2, I can write it as 5.5, which is the compression ratio value, and to the power of 1.4 minus 1. So if I simplify it, T2 is going to be 303 into and 5.5 power 0.4. Okay, so we'll get the value of T2 is going to be approximately 600 Kelvin. Okay, make sure you are using your calculators properly while going for substituting the values in powers. Okay, now we have identified the values for V2, T2, and the value of P2 is already provided in the question itself. Okay, so this is for one process, process 1 to 2, and for the next process, process 2 to 3. So process 2 to 3 is going to be constant volume process, which is governed by the equation V equal to C, and the thermodynamic relations can be written as P by T is equal to P by T, which is P2 by T2 is equal to P3 by T3, or we can simply rearrange this, where P2 by P3 is equal to T2 by T3. Clear? So using these relations, knowing the all values, we can estimate the unknown values. So I will be required to estimate P3 or T3 at the first stage. So without knowing T3 or P3, we cannot estimate the other. Anyone we should note the earliest. So for identifying these values, it has been provided in the question, and another data of heat supplied. Okay, so heat supplied QS is equal to 210 kilojoule. Heat is supplied at this constant volume process during the process of 2 to 3. So during a constant volume process, heat supplied can be written as Qs is equal to m Cv into delta T, which is T3 minus T2. Here we know the value of Cv, which is going to be 0.712 for air, and T2 value we have estimated over here 600 Kelvin, and T3 value we are going to estimate. QS is going to be 210, and we need to estimate the value of m. Okay, so the value of m can be written or obtained from the ideal gas equation. Okay, PV is equal to mRT. Since it is given that all the values of state 1 are provided in the question itself, I am taking the ideal gas equation at state 1. Okay, so here the p value is going to be 100 kilopascal and the volume of 0.45 meter cube, which is equal to m value is unknown to us, and for r value we are going to substitute in kilopascal, sorry, kilojoules. So it is going to be 0.287 into temperature is going to be 303. Upon simplification, we will get the m values to be 0.527 kilogram. Okay, make sure that the unit is maintained homogeneously, because here I have substituted this pressure value in kilopascal, so I have substituted this R value in kilojoule per kilogram Kelvin, right? Now coming back to this equation, I will be substituting the values known to us. 210 mass value 0.527, CV is going to be 0.712, and T3 is unknown to us. T4 is going to be, sorry, T2 is going to be 600. So if I substitute and simplify all the values, I'll get my temperature 3 on approximately, it is going to be 172 Kelvin. Okay, having this T3 value using this equation. Okay, so I'm substituting this T3 in this equation. I'll be getting, so I'll just reciprocate this equation. P3 by P2 is equal to T3 by T2. I'll substituting all the known values. P3 is unknown to us. P2 is going to be 1100, right? Which is equal to T3 172 divided by T2. We have estimated that to be 600, right? So if I simplify, I'll get the pressure 3 value to be 2148 kilopascal. Okay, so for the condition or for the state of 3, we have estimated T3 and P3. What about the volume? We know that V2 to 3 is going to be a constant volume process. So V3 is equal to V2. Clear? So I'll be using the same value as 0.0818 meter cube. Clear? So for process 1 to 2 and for process 2 to 3, we have calculated the required values. And similar fashion, we are going for process 3 to 4. Once again, a reversible adiabatic process. So which is governed by the equation of process 3 to 4 PV power gamma is equal to constant. So I can state that P3 V3 power gamma is equal to, sorry, gamma equal to P4 V4 power gamma, right? So do we have all the values? Supposedly not, right? So if I just make it as a pressure ratio and volume ratio, going to be P4, sorry, I will simply make it as P4 by P3. P4 by P3 is equal to V3 by V4 power gamma, right? So this can be simplified as something else. Why? Because is that from the cycle we know that process 4 to 1 is going to be a constant volume process. So my V1 is equal to V4. Similarly, process 2 to 3 is going to be a constant volume process. Q2 is, sorry, V2 is going to be equal to V3. So what I'm going to do is instead of V3 I am putting V2 over there, instead of V4 I am putting V1 over there and whole power gamma. So we already calculated this value. V1 by V2 is going to be R, and for V2 by V1 it is going to be 1 by R power gamma. So my P4 is going to be P3 into 1 by R power gamma. The P3 value we have estimated in the previous step, where it is estimated to be 2148 kilopascal. Okay, so it is going to be 2148 into 1 by 5.5 whole power 1.4. If I simplify it properly using a calculator, I'll get the value of P4 to be 197 kilopascal. I believe you guys are getting the same values, right? Right. Now, moving on to the other relations from the same adiabatic process, I can write it as T4 by T3 is equal to V3 by V4 whole power gamma minus 1, similar to that of your process 1 to 2, right? So instead of V3 by V4 I can simply write 1 by R, so which is going to be 1 by R power gamma minus 1. Clear? Now I am substituting all the values known to me. T4 by T3, you know the value of T3 as 1172 Kelvin. 172 equal to 1 by 5.5 whole power 1.4 minus 1. I'll get my T4 to be simplified properly 591.8 Kelvin. Hope you are all getting the same values as well. Okay. If you want, you can calculate the value of V4 using the ideal gas equation, or as we already stated, V4 is equal to V1. So V4, which is equal to V1, value of V1 was given on the question itself, 0.45 meter cube, right? So we have simplified the values up to whatever the values that we have been asked for in the, okay. So the first equation has been completed. Since the first question have been completed, the rest of the things are going to be like very easy. The percentage clearance. So what we need to do is we need to estimate the clearance volume as a percentage of the swept volume. Okay. So percentage of clearance or percentage clearance, which is equal to VC by VS into 100. Okay. So VC can be written as V2, right? The clearance volume is going to be the minimum volume, and for swept volume we already know that V1 minus V2, which is the total volume minus the clearance volume, which is going to be equal to the swept volume. So V2 value we know, and it is going to be 0.0818 divided by V1 initial volume is 0.45 minus V2 0.0818 into 100. So the percentage of clearance volume is estimated to be 21.95 percentage. Be clear? Next, what we are going to estimate is the efficiency. Okay, the efficiency equation for Otto cycle, eta is equal to 1 minus 1 by r power gamma minus 1. 1 minus 1 by 5.5 whole power 1.4 minus 1. Upon simplification, we will get efficiency in a decimal version, which is 0.495. If I write it in terms of percentage, efficiency is going to be 49.5%. Clear? So the efficiency have been estimated. Mean effective pressure P mean is equal to W by V1 minus V2, where the W can be estimated using the long relation that you have derived for Otto cycle, or I can also make use of the basic equations heat supplied minus heat rejected. Since heat supplied is already known to us, heat rejected can be easily determined. Okay, where the heat is getting rejected, it is being rejected at the constant volume of 4 to 1 process. Here heat is being rejected, right? So what I can do is I can use this particular process for determining the amount of heat rejected. Okay, so amount of heat supplied is going to be 210 minus, for a constant volume heat transfer, m cv into delta t, where t4 minus t1 is going to be used. So I have known all the values, right? We have estimated all the values earlier in the first subdivision. Now the value of 210, substituting the value of m 0.517, I think so, right? CV is going to be 0.712, and T4 we have estimated in the previous step, right? T4 was 591.8 Kelvin, 591.8 Kelvin minus the initial temperature is going to be 303 Kelvin. I'll just go with the final answer. W is equal to 104 kilojoules, right? So using this simple method, you can estimate the amount of work done, or we can also go for the traditional equation. W is we have the long equation in terms of pressure, compression ratio, and other values, right? So here I have gone for the simplest version. So coming back to mean effective pressure, P mean is equal to W by V1 minus V2. W has been estimated as 104 divided by V1, which is 0.45 given in the question. V2 0.0818, which we have estimated in the earlier steps. Upon simplification, we will get the mean effective pressure to be 281.8 kilopascal. Make sure you guys are making use of your calculator properly. Again and again I'm saying that. Next thing what we are going to estimate is the power developed, right? Which is the power developed per cycle, right? That is what asked in the question paper. Power developed by ideal power developed by the engine. Okay, and the number of cycles is 210 cycles. Okay, so the power developed is going to be estimated from the relation work done per cycle. Okay, work done per cycle multiplied by number of cycles per second. Clear? Now we have calculated the value of work done per cycle, which is going to be 104 kilojoule. Okay, 104 kilojoule, and number of cycles is given as 210 cycles per minute. Okay, but here we need that in seconds. So for converting that minute into seconds, we are multiplying the denominator by the 60, so that the number of cycles has been converted into cycles per second. Okay, now the power developed P can be simplified, sorry, obtained by simplifying these relations. So if we simplify further and all, we'll get the values to be 364 kilowatt. Okay,